Good afternoon. This is the Chemistry 101, Chapter 12, ending video. I'd like to pick up with where we left off with ketones. Name for each ketone: those carbons that contain that carbon chain, the longest continuous unbroken carbon chain that contains our C double bond O. So this is 1, 2, 3, 4, 1, 2, 3, 4, 5. The longest chain here is a pent. Where is our C double bond O? Now we need to decide, is this one and numbering this way, or is this one and numbering this way? We want to give that C double bond O the lowest numbering position possible. So if we start with here, it's 1, 2. But if we start from this right and work left, it's 1, 2, 3, 4. 2 is less than 4, so it's 2 pentanone. The AN says that in this 5-carbon sequence, that is all totally saturated, alkane-like, no double bonds or triple bonds for the compound. So we've taken care of this. What's left? We've got the single CH3 group. So it is at 1, 2, 3. It is a single carbon fragment, methyl. So it is 3-methyl-2-pentanone. Number D. Let's see if I can draw this lower because it's hanging right in the reflection. We have a 6-membered ring. It is the parent compound. Since it's cyclic, it is cyclo. 6 carbons, hex. All of the carbons in the ring are totally saturated. They are hydrocarbon-like. They are alkane groups. So it is cyclohexane. If there were no carbonyl, it would be a cyclohexane. But since we have a carbonyl, we drop the E ending and put on the O-N-E ending. So this is cyclohexanone. We don't need to say one cyclohexanone because this is always given the priority group. So this is always at C1. So we don't need to write one cyclohexanone. The carbonyl is always at 1. Then we number around the ring, either counterclockwise or clockwise. That gets us the lowest numbering sequence to our substituents. If we number counterclockwise, 1, 2, 3, 4. So the first substituent would be at 4. If we go around clockwise, 1, 2, 3. So that makes this a 3-ethyl, 4-methyl substitution pattern. At the 3-carbon, there is a 2-carbon fragment. At the 4-carbon, there is a single carbon fragment. That single carbon fragment is a meth. Single carbon fragment is meth. Since it's a piece of spinach, methyl. 2 carbon fragments, it's an eth. 2 carbon fragments as a piece of spinach, ethyl. So it should be, listing these alphabetically, E comes before M, 3-ethyl, 4-methyl, cyclohexane. So 3-methyl-2-pentanone, 3-methyl, 4-ethyl, 3-ethyl, 4-methyl, cyclohexanone. Physical and chemical properties of aldehydes and ketones. They have higher boiling and melting points than similar hydrocarbons because they are polar molecules. They have dipole-dipole forces. They do not have hydrogen bonding, but they have more than just the dispersion forces as the alkanes do. Aldehydes and ketones have lower boiling and melting points than alcohols because they do not have the proper structure for hydrogen bonding. Because they have weaker intermolecular forces than alcohols. They have lower melting and boiling points than alcohols, but higher melting and boiling points than the corresponding alkanes. Generally, aldehydes and ketones are soluble in organic solvents. Again, the limitation is right about the 6 carbon cutoff. Those molecules with less than 6 carbons are generally, so the C5 and below, are soluble in both organic solvents and water. But those aldehydes and ketones that have 6 carbons or more are not soluble in water. They're still soluble in organic solvents, but they are not soluble in water. Aldehydes. Talked about reduction. We talked about oxidation. Again, oxidation. We can represent that by the open bracket, capital O, close brackets. Aldehydes contain an oxidizable hydrogen. So this bond can be broken and be replaced with an OH bond. So the aldehyde can be oxidized up to the corresponding carboxylic acid. In oxidation, the aldehyde hydrogen is converted to an OH bond. So we oxidize up butanol to the corresponding butanoic acid with a chromium-based reagent. Again, your chromium reagents are your primary reagents of choice to do oxidations from aldehydes or alcohols up to the corresponding carboxylic acids. Ketones cannot be oxidized because there is not an oxidizable hydrogen on that carbon to be removed so that we can form another bond to oxygen. So the ketones are not oxidized via any reagents because they do not have that removable hydrogen. We talked about this in the lab today. However, unfortunately, we did not get to it before the lab started. When we're talking about molecules and their interior designs, there's a unique feature about molecules in that sometimes they can be mirror images of one another, just like the right hand is the mirror image of your left. You can put them together and the right hand is reflected in the left hand, but they are not superimposable. The nail points in that direction. This hand, the nail points in that direction, so they are not superimposable. With my left hand, the palm is facing me, but I can't get my right hand in any way such that its palm is facing me also and still have the thumb in the same direction as on my left hand. So these are mirror images. So our left hands and our right hands are mirror images of one another. But the left hands and the right hands are not identical. They are not superimposable. So we see that the thumb of one hand sits here and the thumb of the other hand sits there. There's no way that we can twist or without severing the body part, and that's not fair. That's outside the rules, where we can get these thumbs to be identical positions with the identical relationship to one another. We can look at the overall structure of the molecule and say that if it is not superimposable on its mirror image, that molecule is chiral. We can have two mirror images that are superimposable, like socks. These are superimposable upon one another. A molecule that is superimposable on its mirror image is achiral or not chiral. For instance, let's look at the molecule CH2BrCl. Carbon, black, hydrogen's white, green is bromine, red is chlorine. They are mirror images of one another. We've constructed these two molecules. So this green corresponds to that corresponds to that in the mirror image. But is there any way that we can flip this molecule, top for bottom, left for right, any degree of rotation that we can use to make this exactly like that, to superimpose? Yeah, there is. So with the green green and the red red matching, this molecule has a mirror image, but its mirror image is superimposable upon the other one. Therefore, this carbon is not chiral. It's achiral. If we take the molecule methylfluorochromo, excuse me, bromo, chloro, fluoro, methane, ClBrFH, we make that molecule and we make its mirror image. These are mirror images of them, but there is no way that we can rotate either up, top to bottom, side to side, front to back. There is no way that we can rotate this molecule such that everything here lines up there. So if we match the yellow and the black, the red and the green don't match. But if we match up the red and the greens, the whites and the yellows don't match. This means that it is a chiral molecule. Notice, for chirality to exist, we must have 1, 2, 3, 4 different things bonded to that carbon. In this particular case, we have a hydrogen, a chlorine, a bromine, and a fluorine. Those are all 4 different things. If a carbon is bonded to 4 different things, then it is not superimposable on its mirror image. That molecule is chiral. The two mirror images of bromo, chlorofluoromethane are enantiomers. They are mirror images that are not superimposable upon one another. A molecule that is not superimposable on its mirror image is called a chiral molecule. So a carbon atom with 4 different groups, like the bromochlorofluoromethane, is called a chiral molecule. This carbon is chiral. It possesses a chiral center. So because we have 4 different things, hydrogen, bromine, chlorine, and fluorine, bonded to that carbon atom, that's called a chiral center. To locate a chiral center in a molecule, you look at each tetrahedral molecule, every carbon atom in your molecule. If it's bonded to 4 things, look and confirm that if any 2 are the same, you do not have a chiral center. But if you have 4 different things, you do have a chiral center. So you look for 4 different groups bonded to your carbon. Most of the time, you can look immediately at those things that are bonded to the carbon atom. You can do that for many cases. Other times, you have to look and see, well, maybe this might be a carbon, this is a carbon, that's a carbon, and that's a carbon. But you have to go further than that to see if the molecule is chiral. Let's say we have that 4 carbons. We have an H, a CH3, a CH2, CH3, and a CH2, CH2, CH3. So let me redraw that. H, CH3, CH2, CH2, CH3, CH2, CH3. Okay, carbon, hydrogen. Is there any other immediate hydrogen connected to that carbon? No. If we go to these 3, there are carbons. They are all carbons. But what are each of these carbons bonded to? Well, this carbon is bonded to 3 hydrogens. So HHH are the three things connected to this. To this carbon, we've got CHHC. Well, this is not the same as that. But what about this guy? Is this different than that? Well, the first bonding, we have CHHC. So CHHC, CHHC. Those are identical. Go to the next group. What is bonded to that next carbon? So we've identified and couldn't do anything there. Go to the next carbon. What is this carbon bonded to? That carbon is bonded to two hydrogens and another carbon. So the connectivity here is CHH. We're looking at what's bonded to that carbon. Now we're at this guy. HHH. Is CAH the same as HHH? No, it's not. So we have four different things. This hydrogen, this methyl, this ethyl, and this propyl group. Again, many times you can easily look at what is directly bonded to your carbon atom, and many times you can see four different things. But sometimes you need to see what's bonded further out from the things that are immediately bonded to the carbon that you think may be chiral. Again, let's look at this. We have 3 bromohexane. 1, 2, 3, 4, 5, 6. 6 carbons, longest chain. 1, 2, this is at the 3 position, so 3 bromohexane. This carbon is bonded to a hydrogen, a bromine, and a CH2. But what are these two CH2s bonded to? This carbon is bonded to a carbon with 3 hydrogens. Sorry, this carbon right here, label it A, is bonded to a carbon and 2 hydrogens. Those 2 hydrogens right there and that carbon. Call this A prime. A prime is bonded to a carbon this is A prime, is bonded to 2 hydrogens and a carbon. So what's bonded to this? What's bonded to this carbon? HHC. CHHHHC, same thing. What is this CH2 bonded to? A carbon that has 3 hydrogens. This carbon out here now we're looking at these pairs. What is it bonded to? Bonded to 2 hydrogens and another carbon. Well, this is bonded to 3 hydrogens, H, H, H. This is bonded to H, H, C. So the presence of the CH3 makes this different than that. Since this is not a CH2 group, this is a CH3 group. We have 4 different groups. Therefore, this carbon is chiral. So we have the hydrogen as one group, the bromine is the second group, the ethyl group is the third group, and the propyl group is the fourth group. So we have 2 different kinds of alkyl groups, a C2 and a C3, the bromine and the hydrogen. This carbon is bonded to 4 different things. The presence of chirality centers is a very important thing for reactivity in organic systems. If we look at tartaric acid, these two carbons are chiral. This carbon bonded to a hydrogen, an OH, and a C double bond O. Is this an H, an O, or a C double bond O? No, it's just a carbon. So there are 1, 2, 3, 4 different things bonded to that carbon. This carbon is bonded to an H, an OH, a C double bond OH. Is this another C double bond OH? No, it's not. This carbon is bonded to 1, 2, 3, 4 different things. That carbon is chiral. We can look at ephedrine. This is the precursor that illicit manufacturers of methamphetamine producers use. This carbon, if we look at it, we have a hydrogen, an oxygen, a carbon involved in an aromatic ring. Is this carbon involved with another carbon involved in an aromatic ring? No, there are no double bonds that carbon is involved with. So 1, 2, 3, 4. If we look at this carbon, it's bonded to hydrogen, to a nitrogen, to a CH3 group, and to another carbon-containing group bonded to an H and an OH. Is that bonded to an H and an OH? No, it's bonded to 3 hydrogens. So we've got 1, 2, 3, 4 different groups. Both of those carbons are chiral. And it turns out that chirality centers have levels of activity that are important in biological systems. Ephedrine, or its isomer, pseudoephedrine, is a bronchodilator. It opens up, it dilates, it makes it bigger, the blood vessels surrounding the heart. So the pressure for pumping the blood, i.e. the blood pressure, is lowered. There's certain ways that we can draw these molecules that gives us an idea of the relative position three-dimensionally with respect to one another. A Fischer projection takes a three-dimensional tetrahedral shape and redraws it. A carbon atom is located at the intersection. So this is a Fischer projection. So we have these two cross lines. Where this carbon is chiral, it has four different things attached to it, the lines cross. This Fischer projection implies that Z and X are coming out towards you. These are pointing into the room. Z and X lie forward of the blackboard. Z and X lie forward in the room. W and Y lay back behind the board, sticking out into the hallway. So these horizontal bars with this wedged line come forward into the room. These vertical dashed lines go back out into the hallway. We can equate these things such that Z and X are left and Y. Z and X are left and right. W and Y are top and bottom. So the horizontal bonds, Z and X, come forward into the room. The vertical lines, W and Y, go back behind the board. This allows us to draw mirror images. These are called Fischer projections. So we can draw these Fischer projections and the dash line and the wedge line structures for 2-butanol. Hydrogen, OH, CH3, and CH2, CH3. 4 different groups. This particular isomer of 2-butanol has a chiral center. we are drawing what we are representing on this side of the mirror, what the mirror image would look like. So we've got the CH2, CH3 coming forward. We've got the CH3 coming forward, but it is behind this carbon. So we flopped the CH3 over here. The H and the OH are still back and going into the board. If we replace these with the Fisher cross, we see the H and the OH are up down. But now we see the CH3 is to the left, CH2, CH3 is to the right in this isomer. In this isomer, the CH3, CH2 is to the left, and the CH3 is to the right. So it's important that you get some concept and understanding of the information that is present in these Fisher types of representations. Many drugs have chiral centers, and often they must interact with a chiral receptor to be effective. One specific isomer of a drug may be effective in treating a disease, while its mirror image may not have the effect that we'd wanted. A particular horrific story comes from the thalidomide, Thalamide, thalidomide. Thalidomide was a drug used from the early 20s until basically the late 50s or early 60s. It does wonders for pregnant women to suppress nausea. The only problem is thalidomide can come in two different isomers. One isomer is the one that suppresses the nausea during pregnancy. The other isomer, unfortunately, has horrific effects for limb development. People are born without arms or without legs, or half an arm, or an arm but no hand. So they did not find out until there were a lot of individuals that were treated with thalidomide, but then ended up having children with deformities. The way that we can say why one isomer worked and the other one did not is based on its shape. One of the enantiomers may fit a specific site where activity is controlled, so it can evoke a specific response. The mirror image, the other isomer, may not have the same physical shape, that it does not fit, therefore does not cause the effect that we are looking for. Here we have phenylalanine. One specific isomer, the other specific isomer. Here we have a template. This template, it represents what the receptive site, the physical constraints that have to be present for something to fit into the chiral receptor site. So we have to have this big planar CH3. We have to have a small group right here and something big enough and polar enough to match with the C double bond O. With the C double bond O, OH, because that's what this represents. Its mirror image, though, does not have the correct orientation. This small hydrogen group is not there, it's here. This carboxylic acid group is not there, it's here. So if this big planar group fits down like this, neither the small hydrogen or the carboxylate group do not fit into this pre-designed chiral receptor site. So this is why only one particular isomer of one compound may have the activity and the other one does not, because the molecule itself does not have the right fit or shape to fit into the substance that triggers the activity. That's chapter 12. That ends chapter 12. Hopefully you'll be able to pick this up and watch and connect with the chapter 12 lecture. See you guys later. Have a good evening.